Plus, rumours and counter-rumours about Hinkley Point Power Station. What's happening to the waste from Hinkley A, which was decommissioned in 2000? Is Hinkley B really a bomb factory, as we heard from Nicky Clark from the campaign group Stop Hinkley last week? And will Hinkley C ever be built? On our story to do with Hinkley Power Station, I'm joined on the line now by nuclear engineer, retired, John Large. Hi, John. Welcome to the Politics Show.
Hi.
Can I just ask you about what your thoughts are about the progress of Hinkley C and whether ultimately you think it's ever going to be built?
Well, there are a number of factors on Hinkley C. I mean, the primary one is this, is whether the government has got enough confidence in the Chinese to actually back the project in terms of cash injection. You're talking about a project that's going to cost 20 or so billion pounds in the long run, and it's a long haul. It's going to occur right up until about 2023. That's the headlines that have been occurring. But underlying that are a number of difficulties. One of the difficulties is the strike price, the very expensive, nearly £100 per megawatt generated strike price that the government has negotiated with EDF. In effect, it's guaranteeing EDF over the next 30 or so years, when this station comes on to generation, if it does, a price that is roughly twice the price we pay for the present for electricity. So it's offering the operator, EDF, twice the price of the current generating cost. And underlying all of this is the technical aspects of what's occurred in France and in China. What has happened, there's the identical reactor, virtually identical reactor, is called the EPR, the European Pressurized Reactor. That's the type of reactor that's going on at Hinkley C. They've been built in France. It's been one being constructed in France at a place called Flamanville, down in Normandy in that area. And there's 4 being built at Taishan in China. Well, we know the one at Flamanville has developed a major technological, in fact a metallurgical problem with its pressure vessel. This is an enormous piece of steel work, weighs about 700-800 tons, and it's developed what's called a carbon anomaly. I mean, let's not go into technical details. And what it means is, because the manufacturing, particularly the forging stage of this particular pressure vessel in France, the components that were built in France, means that there's excessive amounts of carbon, free carbon, out of solution in the grain boundaries of the material, of the steel. What this has an effect to do is makes it very brittle. So instead of being a ductile material still, it becomes rather a glassy material. It's very difficult for engineers to actually determine when it will foul in terms of our pressure load overload. So the problem is this, that the French nuclear safety regulator has dictated to EDF, the same operator in France as in Britain, that it must demonstrate the wholesomeness of the pressure vessels at Flamanville. Unfortunately, the pressure vessel at Flamanville was inside its containment, so it can't be got at. So what they're going to do is they're going to use the production model for Hinkley Point C, the pressure vessel that's already been made, as a test piece. And this will put back, and that means it will be destroyed, and this will put back the manufacture of a new pressure vessel, pressure vessel components, for about 3 or 4 years. So there's a big doubt now whether actually Hinkley Point, even if the order is confirmed and endorsed and sponsored by the Chinese, there's a big doubt that it could actually come online by 2023. And of course, if it misses the 2023 boat, effectively Britain runs into a calamity on the supply and demand of electrical generation and demand.
I notice also that Hinkley B is going to due to be decommissioned in 2025, so it's to be a very narrow window to actually keep any kind of nuclear production going at Hinkley.
Well, there's some doubt whether Hinkley B will actually reach 2025. I mean, the Hinkley B reactors are what's called an advanced gas-cooled reactor. They're a development of the old Magnox reactors, and they were designed quite specifically for a 30-year life. And 30 years was up for Hinkley Point B in about 2006. So it means that they're stretching the serviceability envelope for Hinkley Point B well above what it was originally designed for. And there are significant problems with the AGRs as they age. And one, these are not reversible problems. You can't get into the AGR reactor to do an in-situ repair. You can't replace bits and pieces inside. And what's particularly worrying about the AGRs at Hinkley Point is a cracking that's developing in the graphite core, the moderated core inside the reactor pressure vessel, which is enormous. I mean, 20 meters in diameter. Inside there is a graphite moderated core, which is effectively, it slows the neutrons down so the nuclear process can go on. But really, what it is, it's a loose stack of bricks, graphite bricks. And what's happening to those bricks is they're cracking. They're cracking vertically. So it's very difficult now for engineers to work out what the residual strength of that stack of bricks is inside the core. Should there be a sudden pressure aberration going on, like a loss of coolant accident, what would happen to the core? Would it misalign and distort, trapping the fuel and causing a fuel meltdown and, disaster scenarios like that? So there is some doubt whether Hinkley Point B will actually fulfill its 40-year life requirement.
Also, on this show last week from Stop Hinkley, Nikki Clark was telling us that the plutonium that comes from these factories, which is, she called it a bomb factory, it has to be replaced in the nuclear weapons every 3 or 4 years. I wonder what, is that accurate, John?
No, that's a misunderstanding. I mean, first of all, there's a number of misunderstandings there. First of all, the plutonium generated by the advanced gas-cooled reactors in their fuel, to extract plutonium, you have to irradiate, in other words, put uranium fuel into a nuclear reactor. And this gives you a very small percent, less than 1% of plutonium in the irradiated, highly radioactive fuel that has to go to Sellafield to be reprocessed. The advanced gas-cooled reactors are not particularly good plutonium breeders. So that's the first thing. And most of the plutonium that Britain uses was gained from the Magnox program, like Hinkley Point A. It was gained from those reactors, and it's fairly stable. In terms of once you've actually extracted the plutonium at Sellafield and gone through a series of refinements, the plutonium goes into the nuclear weapon. It's called the fissile pit. And typically the present generation of British nuclear weapons is got a shelf life, an operational shelf life of about 12 to 14 years. So there's no need to replace the plutonium or to do any refinement of the plutonium in a British nuclear weapon for about 14 years. In fact, the thing that has to be replaced is what's called the tritium, which is another radioactive, a radionuclide, the tritium booster pack that actually gives the atomic part of a thermonuclear weapon a boost to get a lot more energy out of it. So,
what about the point about, is it a bomb factory, John?
What, Hinkley Point? No. It was acknowledged by the old CEGB, the Central Electricity Generating Board, that up until the 70s, that the civil nuclear reactors, primarily the Magnox reactors, were part of the plutonium yield program. But since that time, Britain has such an enormous stockpile, well over 100 tons of plutonium. In fact, we have more plutonium than we need. And there's two stockpiles. There's the military stockpile, which is dedicated to the nuclear weapons. Then there's the civilian stockpile that's supposedly separated from the military stockpile. It's safeguarded against entering the nuclear weapons cycle. It's all part of the Non-Proliferation Treaty. So you separate out the civilian material that comes from places like Hinkley Point A, used to, and Hinkley Point B, and for that, the nuclear industry is planning, although not particularly successfully, planning to actually use that in an adapted form, a pressurized water reactor called a MOX-fueled reactor, a mixed oxide-fueled reactor. So the industry has laid aside plans to actually use the surplus uranium yields that it gets from the irradiated fuel coming from nuclear power plants like Hinkley B and also from Hinkley C, if the fuel contracts are signed.
What about Fukushima? That's another thing that's on everyone's minds at the moment. I wonder what your thoughts are about what's happened here. We've had news just this week that it looks like there's a large amount of nuclear fuel which has disappeared, and people are suggesting that possibly that fuel has somehow melted down. What's your analysis of what's been going on over in Japan?
Oh, it's quite clear what's happened to Fukushima. Effectively, there were 6 reactors, 6 nuclear power plants at Fukushima. 3 of those were operational and utterly destroyed during the tsunami events, the post-tsunami events. 1 other reactor, reactor number 4, Unit 4, that was destroyed, although it was defueled at the time. It was destroyed because it was coupled to another reactor, Unit 3. What happened in Fukushima was that the earthquake occurred and the reactors quite properly shut themselves down. The earthquake destroyed the local electricity grid, the number of pylons that you see going into any power station. When the power plants close down, they're dependent upon the external electricity supplies to actually run their pumps to maintain cooling. And a nuclear reactor has to be cooled for days and weeks, in fact years, after it's closed down. So you have to use electrical supply. So what happened was the earthquake came along, it destroyed, the reactors closed down, as they do automatically under a seismic shake. The earthquake was so severe, it destroyed a lot of the grid system, the electrical distribution system. So the reactors at Fukushima Daiichi went on their electrical generators, their emergency generators. These are big banks of diesels that run generators to supply that electricity required for the pumps inside the station. That was fine. That was running for about 40 minutes. Everything was fine. The reactors were being cooled. Things were under control. And then the tsunami hit. And the tsunami then flooded the site, because it's a coastal site, and they put the generators out of action. And then after that was 40 minutes after the earthquake, after that, 3 of the reactors melted down, and the meltdown occurred within 40 minutes of the tsunami striking, and within 40 minutes, the fuel cores, those 3 fuel cores, were committed to melting down. Within 6 hours, they'd melted completely. The fuel itself, about 100 tons of fuel, had slumped into the bottom of the reactor pressure vessel, and then it began to burn its way through the 150 millimeters or so of reactor pressure vessel still worked, and then after about 18 hours, it slumped onto the concrete floor of the containment inside the reactors inside a containment. And what then happened was the red-hot molten fuel running at about 1300 degrees C, which of course is generating heat because of its radioactive decay, it then started reacting with the concrete floor of the containment, and it generated carbon dioxide gas, which is a non-compressible, non-condensable gas. In other words, once you've got a pressure of it, you can't cool it to reduce the pressure. And that pressure of non-condensable gases then ruptured the containment. We saw on Reactor 1, Unit 1, and Unit 3, it blew the roof off the containment. And the interesting one was Unit 2, where the explosion breached the underground part of the containment. That Unit 2 has let in a lot of groundwater, and the groundwater has washed over the slumped reactor core, which is called corum, this molten fuel core. And of course that is a transport mechanism to take, via the water, to take lots of radioactivity, a tremendous amount of radioactivity actually, into the ocean, into the marine environment.
Well, that's really worrying, John. I mean, what are your thoughts about the possibility of that actually, spreading around that part of the world? Because once it's in the sea, it could go anywhere. Well, what happens is you can see what the mechanisms are, because if you get it into the sea, these are tiny particles of fission products, radioactive products. Things like filter feeders, molasses and things like that, and fish, they will gobble this up as protein. They can't distinguish between iodine, natural iodine, and iodine-131, radioactive iodine, or cesium and radioactive cesium. So they gobble it up, they reconcentrate it in their organs, and they become radioactive. And of course, if humans then start eating the clams and things like that, they become radioactive. They take in the radioactive food. So, typically a fish can reconcentrate the amount of radioactivity in the sea surrounding it by about 15 to 20,000 times.
a clam, a filter feeder, can do it 100,000 times. So you can, by this natural process, going through the food chain, contaminate the human population. Another problem is this, is the tidal line. If you have radioactivity, the flotsam and jetsam of radioactivity from a reactor contaminated the sea, things like seaweed, etc. As the tide comes in, it leaves an intertidal deposit. We've all walked along a beach and seen the debris along at the tide end. And of course, the intertidal deposit dries out between tides, and then you get onshore and offshore winds blowing the dried out particles. They become air suspended again, and they can then contaminate, as an airborne dispersion, contaminate local seaside communities. So it's a very complex mechanism by which the radioactivity can leave the reactor once the containment's broken, get into the marine environment, and then become atmospherically dispersed again.
What are your thoughts about the way the Japanese government and TEPCO have coped with, and have they been honest with the public about this disaster?
Well, we saw panic, we saw lack of planning, and we saw the consequences of lack of planning. The consequences of not recognizing that catastrophic events can occur. The Japanese nuclear safety regulators have taken much the same stance that's adopted universally, internationally by regulators, including our own regulator, the Office for Nuclear Regulation, that you can actually, it's within our wit to actually predict the frequency and severity of accidents. In other words, we convince ourselves that we can say how often very severe accidents will occur. And we say if the frequency of a severe accident is, say, a million, once in a million years, then we can say that accident is so remote we can consider it incredible. So we don't have to plan for it. So in other words, we say, of course you can have an earthquake and a tsunami, but it will be so remote, it's not worth planning for it because it will never happen. Or you could say, I know black swans exist in New Zealand, but I'm never likely to see one. So in other words, I can take no account of it. I don't have to take account of it. And that was a problem. That was a problem in Japan, was that the nuclear regulator became convinced that its forecasting of what could happen, the severity and frequency of the events, it didn't put in place proper contingency plans to counter those events. And that event, of course, was a tsunami, an earthquake. And of course, in Britain, it may not necessarily be an earthquake or a tsunami, or it could be a tsunami, it may not be a tsunami. What it could be is the accident and severity that we hadn't thought of. Well, and that's the real question here.
That's the commercial nuclear world, which is rather more open than the military world. One does worry, doesn't one, about the amount of stockpiles of plutonium and whether that stuff ever goes missing, because I know there's certainly been reports about nuclear weapons even being dumped in the sea under difficult circumstances and then not being able to be retrieved. I mean, do you think there are nuclear weapons out there that have gone missing?
Well, there's certainly nuclear weapons that have been dumped in the sea. I mean, I worked on a submarine called the Somerset, a Russian Federation submarine that sunk in 1989, and she had 4 nuclear weapons on board. The Americans have lost a submarine with some nuclear weapons on board. So, yes, of course. And, of course, there's been some aircraft crashes where nuclear weapons have been lost at Palomares in Spain. There were 4 nuclear weapons jettisoned. And those were all recovered slowly, but 2 of them caught fire and had a contamination. There was another serious nuclear weapon loss at Thule in Greenland, and so on and so forth. So, if you play with fire, you're bound to burn your fingers.
Certainly, gamma radiation burns nasty. But, I mean, you worked, didn't you, on a programme back in, I think it was 1993, with Roger Cook called Dirty Bomb, and that was looking at the post-Soviet era in Russia and surrounding countries, and there were a lot of military people that hadn't been paid, and yet they were in charge of nuclear weapons. And I know as part of that programme, Roger was actually offered weapons-grade plutonium. Just to tell us, I mean, am I right in thinking you were involved in that programme?
Yes, yeah. Well, we We put together a suitcase bomb, actually. A model of one, I would add.
That does seem to indicate that actually this kind of, very dangerous weapons-grade plutonium was available on the black market, for goodness sake.
Well, it's not necessarily... It's the responsibilities of the nuclear states to make sure that proliferation in any form doesn't go ahead. And the real problem becomes if a subnational terrorist group, with the back-in of a state, can acquire a weapon and acquire the means of detonating it, then we have a major problem. And that is causing serious concern generally among all the superstates, because the superstates, and I mean the superstates like Russia, United States, Britain, France, etc., see themselves as potential targets for that sort of action. So one could see the question of weak links in the proliferation controls as a means by which terrorists could create a devastating effect on a country. The other option is, of course, is to use the existing nuclear facilities themselves to create the same radiological havoc by using the pent-up, the locked-up energy of a nuclear reactor to trigger it into a release situation. So in other words, one of the problems with nuclear power plants is that in the past they've been designed primarily to counter accidents. They've been designed primarily to resist accidental events. That's unintelligent accidental events. What has changed in the last decade is we now know that nuclear power plants are considered to be viable targets by some terrorist groups. So now they are potentially not going to be subjected to an accidental event, which is an unintelligent, random event. They could be subjected to an intelligent, intentional event that seeks out the vulnerabilities of the plant. Now, if the plants were not designed in the first place to actually resist intentional, intelligent events, then we have a problem. And many of the plants, not just in Britain, but in internationally across the world, were never designed to resist terrorism.
You seem to be saying, John, that this technology is inherently unsafe. Is there any real possibility of actually reining the technology back now? It's like Pandora's box has been opened.
No, there are a number of technologies that are inherently risky and have hazards. So nuclear power is not the only one. There are many. As we probe into advanced technology, then we have to take risks. The problem is, to my mind, is who should judge whether that risk is acceptable? Should it be the state without that much consultation with the people, or should it be the people with some consultation with the state? And at the moment, it's clearly the state makes the decision on our behalf. It says what it considers to be a tolerable, what it considers to be an acceptable risk of accident or incident, and what it considers to be tolerable consequences. It really doesn't consult the public on what risk it would want to take and what consequences it would wish to bear in terms of an accident. And that's really what's wrong here, is the public should determine what the acceptable risk is and what tolerable consequences are.
What do you think the relative risks are of some sort of unintended use of a nuclear weapon compared with that of a power station? Because, maybe we've just been lucky over the last 70 years or so that it's only been the nuclear power stations that we've had accidents with.
Well, who knows? I mean, it's a determined, if you have a determined person, individual, then who knows? I mean, what's the saying? The state has to be lucky all the time, the terrorist has to be lucky just once.
OK, retired nuclear engineer John Large, thanks very much for joining us on The Politics Show.
Thank you.
You can listen again to any shows at bcfmradio.com and leave comments about your favourite programmes. BCFM 93.2, your interactive station 24 hours a day.